Welcome back, everyone, to this third episode. I'm trying an experiment here, and I'm down here. Can you see me here? On the side, I thought, just a disembodied voice is not as compelling, and there's some free space here. As a matter of fact, I can actually make it bigger because, yeah, I don't need to show that stuff in there anyway. I'm not hiding anything really important. Yeah, there you go. Here I am. The plan for today is twofold. Now I'm in the way. It's twofold. Is to look at this additional material here on the top, and there are two more LED drivers at the bottom. And the reason for that is we need to drive the LEDs correctly in order to see the signals. And I also want to be able to use this board as a standalone hand calculator. So I've added dip switches here and more drivers for the LEDs on top. So the reason is twofold, is to drive the LEDs correctly and to allow for a standalone mode of use of this card instead of having a card that only really ever works inside the system. I wanted it to be autonomous in a different mode as well. So that's what we are going to discuss. But before we get to all that, I want to tackle, let me move myself around again. I want to tackle a couple of questions I got in the previous videos. One question I got twice, which is, why am I using, in the schematics, why I'm using entire chips instead of doing a low-level schematic with, sorry, let me move myself again. With individual gates, NANDs, XORs, ORs, and all that, like the old-fashioned way. There are a number of reasons for that. One is the purpose of the simulation is to catch errors before I send this for the PCB manufacturers to make a board. And the place where the errors are made, 99% of the errors will be made in how I connect the pins to one another, how I connect the pins together, actual concrete pins. Because what you see on a PCB, what you see on a board are chips, not abstract floating individual gates. So I want to capture in the simulation the error-prone process of defining the netlist, defining how pins connect to pins. And if the simulation runs correctly, then I will know that I connected everything correctly, and then I just move the netlist over to a CAD tool for PCB design without having to think about the functionality again. I just make sure that pin 3 is connected to pin 7 of that other chip, and I do that for every connection. And if everything matches, then I have a high degree of confidence that the PCB design is correct. So that's the reason. The only motivation to run a simulation at this point is to make sure that the board design will be correct, and boards use chips, not floating gates. There was one particular commenter that when I explained this, he seemed to have gotten upset and went on a tirade saying that everybody designs, even today, still with individual gates in schematics. Sorry, that's complete and utter nonsense. This person just doesn't know what he was talking about at all. There is only one circumstance in which designers still today will specify a circuit at the level of individual gates. Not in schematics. We will always do that in a hardware description language like VHDL, Verilog, or Couple, a hardware description language that allows us to specify a circuit at the level of individual gates by writing commands, because it's much less error prone than trying to draw schematics. But even that will only be done when we are designing what we call random logic or noodle logic, which basically means fine-grained and irregular logic, which is what you usually get when you're implementing a large finite state machine with lots of encoded states, and you have some Carnot map optimized logic on the side. So you want to make sure that you got your logic right first. So then you run a simulation at the level of individual gates without schematics. You just run that in a hardware description language. And then you move to something like this, a board level schematics, to make sure that your netlist, your board level netlist is correct. If you don't do a simulation at this level, you may find yourself having to build a breadboard prototype, which is today not feasible and not practical for most designs. I did it at Cerberus because I wanted to illustrate it, and because I didn't want to use non-public domain models of the complex chips I was using, like the 2 CPUs, the microcontroller, even my own 3 custom chips. Some of those models, you have to get a license for to use in a simulation. Most people would not get that license, so I was catering for what the hobbyist has available. But in this case, we have models for all these TTL chips, all these 74 logic chips. So there is no reason to do a breadboard prototype. And then you have to do it at the level of chips. That's where you want to run your simulation, because that's the only thing that is representative of the error-prone part. So that's the first question. I got another question. Let me zoom in here. And it was about these 2 chips, which are the control logic. Let me open them up. The question was the following. I made quite a point about Schmidt triggers. And this chip here, the 7414, has Schmidt trigger inputs. I made a point about this in episode 2. But for one of the control signals, RLOE, I'm not using Schmidt trigger inputs, because this chip, the 7400, does not have Schmidt trigger inputs. I'm using this NAND gate as an inverter by putting the same input on both input terminals. So what you get on the output is just the inverted input. And I'm not using Schmidt trigger for this one. There are 74 logic chips with NANDs that have Schmidt trigger input, but I believe the one that is available has only 2 NANDs, and I needed 3 NANDs for actual logic, not only to invert something. So I would have to have used another chip to put a Schmidt trigger on everything, and I judged that that was not the right balance. It was not the right trade-off. And the reason for that is that this particular signal, RLOE, once it comes out here, it has a fan out of only 1. Let me move myself again and show it to you. This time I'll make myself a little smaller so I don't have to dance around the screen all the time. There we go. So in this particular case, if I go to magnification of 1, the signal comes here. You see this light green line. Then it goes down here and goes in there. So there is a fan out of 1. This trace has no branches. When a trace branches out and goes to different places with a large fan out, you get a number of unwelcome things. You get a voltage sag, which a commenter taught me this word in the previous video. Thank you for that. I didn't study electronics only in English, so I didn't have a word for voltage sag, which is what happens when you have a large fan out and the chip that is sourcing the signal, in this case, this chip here, the 7400, the chip is not has difficulty sourcing all of that current for all of the other chips that are getting the signal, and then the voltage begins to fluctuate. That's called voltage sag. There you go. Thanks for that. So there will be no voltage sag for this one. It's a fan out of 1. There are no branches. The signal is not, the trace is not branching out to go elsewhere. When traces branch out a lot to go to multiple different places, you get a lot of impedance mismatches on every branch. You get lots of reflections that pile on one another because each branch has a different length, so you get different reflections. You get more EMI because the branches begin acting like little antennas, fractal antennas that go all over the place in the PCB. So those are the signals you have to worry about to take countermeasures, so to say. But this one has a fan out of only 1, so I thought I'm not going to worry too much about this one signal and add an extra chip just for it. So I decided to leave it less protected and save a chip. So it's one of the trade-offs that designers have to do all the time. You might hear another designer tell you, no, I'm not going to tolerate even that, because what the Schmidt trigger compensates for is not what's happening after you drive the signal out, but what happens before you get the signal. When the input signal has oscillations, that's what the Schmidt trigger is for. So it doesn't matter that the signal has a fan out of 1 and the others have a fan out of 9. What matters is what happened before. That's largely true. So I'm giving you a sort of a flimsy excuse for my trade-off. But that's my choice. My intuition and my experience tell me I don't need to go overboard with Schmidt's triggers here. Here, I needed the inverters anyway, so I would either use a 7404 or a 7414. I needed the inverters for this signal. This signal absolutely needs to be inverted. This does too, but I could invert it in the other chip. But this signal needs to be inverted, and this signal here needs one inverted version, this one here. It needs an inverted version. And since this NAND gate is already taken, I needed to invert it somewhere else. So I needed an inverter. So why would I choose a 7404 if I can choose an identical 7414, which does have the Schmidt triggers? So that's what I did. And for these other signals, you really have to be careful. That being the reason you see here, set negative high and set negative low. In both cases, I invert them twice. It goes through the Schmidt trigger input, goes out, and then it goes into another Schmidt trigger input and goes out again. And the reason is these signals shouldn't be inverted. They are not active low, they are active high. But I did want to buffer them, and I did want to put them through a Schmidt trigger if I could, without any extra cost, which I could. That's why I'm inverting them twice, because that means I'm actually not inverting them at all, logically. So this is purely for electrical reasons. I do the same with this other one. You see it goes here, and then goes through two inverters, and then it goes out. So it's double buffered. It absolutely needs to be buffered because these signals have fan outs of 9. Like this one here, it comes out, and then it goes in here, so fan out of 1, then it goes there, let's follow it, it goes here, goes down, fan out of 2, 3, 4, 5, and then on the top, 6, 7, 8, 9. Usually we can tolerate a fan out of 10 TTL loads, 10 5-volt loads, before you start need to buffer in it again. So here we are on the edge, but I felt I absolutely needed to buffer these chips. And since I already had an inverter there, which needed to be there because I needed 2 inverters, I might as well use the other 4 as buffers because of the high fan out of the signals. So that's what I did. The same thing here, you see it's inverted twice. Now this one here. This one also has a fan out of 9, and the signal goes there, then it goes down, and then 1, 2, 3, 4, 5, 6, 7, 8, and then this one here, 9. Again, a fan out of 9. So yeah, you absolutely need to buffer those signals, and if you can use the Schmidt trigger when you're doing that, why not? So that's the reason. All right, there's one more thing I wanted to discuss. In the first episode, I made a very mild critique of Ben Eater and another guy, but I got a lot of flames from 2 or 3 people for whom Ben Eater is some kind of sacred cow, and I offended their sacred cow. Oh, by the way, I want to make this prettier. Can I do that? Yeah. Never mind this. I'll do it offline. And these people got offended in the name of Ben Eater from my criticisms. I thought it was quite gentle. I thought, I expressed my appreciation for all his teaching skills. But since I got the flames anyway, I might as well just, go all out and tell you what I really, really think without trying to sugarcoat it. What I think is the following, guys. I think it's a tricky, dangerous world, a world in which most of us choose to be taught by an amateur, to be taught by someone who is not qualified. I think the entertainment value is there, and there is even educational value, a lot of it, in what Ben Eater does, because again, I said this before, he has this skill of explaining the very basics in a way that makes it sound extremely simple. But it's one thing to be a self-taught person, an autodidact, when you are carrying out a hobby. I have other hobbies. I breed tropical fish in the cold of the Netherlands. So I am an autodidact biologist. I am an autodidact astronomer because I like to image the celestial bodies and then interpret those images. So I am self-taught in other things as well. And I think it's great. We live in the golden age for people who can, for people to teach themselves. That's the age of the internet. We shouldn't waste that. We should learn as much as we can on our own. But it's one thing to learn on your own to perform your hobby, and it's another thing to teach what you are not qualified to teach, and to build a career and a living teaching something you were not educated to even do, let alone to teach. It's a whole other ballgame, I think. And whatever educational value there is in the videos done by somebody who is not qualified to do electronics may be compensated, or maybe even more than compensated, by the wrong impression or the false steps that are conveyed at the same time. You come out of a Ben Eater video thinking electronics is so simple, electronics is so easy, I can do all this stuff. Well, if you think it's too easy to be true, too simple to be true, it's because it is. It is too simple to be true, and that's the danger. You start thinking that you don't need to learn anything else. And in a world in which universities and community colleges are putting their courses taught by professionals online for free, I consider it a real pity that Ben Eater gets 4 million views, while universities like Stanford get only thousands of views for their freely available courses, and some community colleges get only hundreds of views for better material that really explore the real issues. Because you see, we've been doing electronics for well over 100 years, and we've been doing computer science for 80 at the very least. We've learned a lot by making mistakes, by realizing that we haven't thought about certain things that we should have looked at. And a lot of knowledge has built up over this time, which is conveyed to you in a formal setting when you're actually pursuing a technical course for electronics, or a college course, or a university graduate degree in electronics. The teachers know what to watch out for, what knowledge you must have because it's relevant, because you need to think about it. An autodidact often doesn't know what he doesn't know, so he cannot look it up. He doesn't know that those issues are there. And there is no point in reinventing the wheel. I mean, we've gone through 100 years of learning in this, about a century. Why would you have to replicate that on your own and even teach? It's tricky. I'm not saying that Ben Eater should stop doing what he does. I don't think actually it's his responsibility at most. I think it's the responsibility of the audience. It's the audience that made him realize he could make a living out of this, given how many views he gets, given how many kits he's able to sell. I mean, in the pragmatic world we live in, who would waste that opportunity? So he set out to teach something he was not taught, something he's not qualified to do, let alone to teach, because there was a demand, and that's where the problem lies. I'm not even against your watching Ben Eater's videos. Go ahead and watch it, but keep it in the back of the mind that there will be invariably a great many things relevant to what you are watching him do that he's not commenting on, he's not saying anything about, because he doesn't know that he doesn't know those things. All these electrical considerations are just shared with you, using two inverters to do nothing logically to a signal just because of electrical considerations. You will not get that from a Ben Eater. I mean, this is very simple stuff. You will not get a lot more important stuff from him either. But this is just a simple example. Considerations of fan out, considerations of EMI and reflections when a trace will branch out in several places, and what do you do to counter that? And when do you choose a chip with Schmitt trigger and one without, even though the chips are otherwise identical, and many other things? What is the maximum current that can be sourced per pin, and then you cannot just add up that current for all the pins, because the total that the chip can sink into the ground pin it has another value, which is less than the sum total of the currents that each pin can source. How do you interpret the data sheets? How do you interpret the characterization of a part in the data sheets? These are all very relevant things. And without knowing them, you may do things that will work at first. I mean, I was warned that Ben Eater did tell people that no, they should use current limiting resistors for the LEDs. If they hang the LEDs from 74 logic series, not only even that, it's more than a current limiting resistor. You cannot use that pin as a logically valid signal elsewhere in the circuit either. But whatever he said or didn't say, the example I'm about to give you still holds. You can hang an LED from an output pin of a 74 logic chip, even without a resistor, and it will work for a while. Leave it on for several hours or a day, and you will see what will happen. Or even if you put a resistor to limit the current through the LED, but you use that same pin to drive a logic value to another chip, keep it on for a while and running for a while, and then have a look at the voltage levels, and you see that they will be oscillating. They will introduce funny errors to the circuit, which will be a hell of a problem to troubleshoot, because they will be intermittent problems. They will happen now and then. And you will not know any of this, you see. It will work at first, and you will think it's okay, and you will buy a Ben Eater kit. And in that case, you will never know that these problems are there, because who is going to use that CPU a lot for several days in a row? No, nobody. You will run an application of 5 instructions on that once or twice, and you stole it, so you will not even get to see the design errors entailed by that. So this is what I think. You may not like it. A couple of people didn't like that I offended their sacred cow. It's okay. You don't need to watch my videos. I'm not shoving it down anybody's throat. But it's my channel. I will say what I think is appropriate to say. You know, I'm not looking for a large audience. You certainly cannot replace Ben Eater with me, because I have no interest in explaining things that fine low level of detail that he does, little step by little step. I have absolutely no patience or interest in doing that. I am a designer and a restorer who happens to make videos. I'm not a video maker. I'm not out to produce courses. These videos, I am doing them for the mere reason that I would be doing Talos anyway for myself. And for the Computer Museum. So I'm doing Talos anyway, so I might as well talk about it to 10 people who might be interested in following along. Even one person, I would do it for that one person, because I'm doing Talos anyway. That's why I'm doing this, and I'm very aware that I'm catering to people who have already a lot of electronics knowledge, who are experienced hobbyists, even if they don't have formal education in electronics. There are a lot of people who have related education. There are a lot of programmers and computer scientists that I know watch my videos. And I'm catering to these people, intermediary to high-level people, and those are the people I have interest in catering for, because I just cannot bother with the very, very low-level stuff. So you cannot replace Ben Eater with me, but you can follow college courses, university courses made available online for free. Just look for them, and you shall find them. And if my, criticizing Ben Eater bothers you, don't watch my videos. It's perfectly okay. Don't go to my comment section and patronize me as if I were a kid teaching me ethics. Don't bother to do that. I don't have patience for this kind of puerile, nonsensical attitude. So don't bother doing that. You will waste your time. But feel free to not watch me if criticizing things bother you. You don't need to follow me. For the rest of you, let's finally get down to business now. Let me go to Auto. Let's now look at the circuit in more detail, and let's simulate it. I'm going to run the same simulations I actually did before I created a PCB, which is a far from exhaustive test set that I used, but I will show the entire simulation process I did go through. I would go through it again with you, because it gives you an idea, at least, of what I think are the key test vectors, the key things we need to test, what regions we need to check, what are the sensitive spots that, that could be prone to errors in connecting this stuff together. So I'll go through the entire thing with you, even though it's not exhaustive, to give you that impression. So let's get started. All right, here we go. If you notice some continuity issues, it's because I made a break. Real life came calling. Had to solve a couple of things. So from this point down, let me illustrate this. So from this part down, you are familiar with it until here. We've discussed it last time. So here on top, these are the lines from the registers. So that's A high input, B high input, A low input, and B low input. So the only difference here is that they are now driven by a 245. So instead of just taking the traces as they come into this card through the backplane, I boost the signals before using them, which is what we have to do. And then next to it, I added a dip switch, and the reason is the user can choose whether the operand will come from the other board, another board, the register file board, which is this case here, or it will come locally from the dip switches. So I added a dip switch and a driver for each of the 4 registers, so the board can be used locally. That's what you see there. So these dip switches also have their own driver, and the idea is that by controlling the output enable of these drivers here, which come from a control setting called standalone. So if standalone is active, then these drivers here, this, and this, will tri-state. They will go into a high impedance, and there will be nothing on their output. Here, 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 and here. And the output enable of the dip switch drivers, it's the opposite of the other one. So if this one is inactive, this one is active, and this buzz line here will be driven by the dip switch. Otherwise, the dip switch driver will tri-state, and this buzz line here will be driven by the bits from the register file. That's basically it. Now, this bus connects to another driver that drives an LED strip. I will be using discrete LEDs, but here, to avoid complicating the picture, I'm using just an LED bar, and the same for all the others. A driver and an LED bar, here, here, and here. Now, because this driver is connected to the bus, whether the information comes from the register file or from the dip switch, it will be displayed on the LEDs. So one of these 2 drivers will always be driving this bus, and whichever one it is, it has to drive another driver and the ALU circuitry itself. It will still be a fairly small fan-out. This is a fan-out of 2 here. Most of these lines go only to one place. I think all of them go only to one place. That's correct. They all go to only one place. So it's a fan-out of 2. No problem. The 245 has more than enough room to drive fan-out of 2. Notice that I take the logic level from here to send to the ALU instead of here. Even if you use current limiting resistors to drive the LEDs, which is what you should do, 1K ohm resistors at 5 volts, that will give you 5 milliamps. That's enough to give you enough brightness for the LED. But even though there will be this current limiting resistors in the PCB, I'm still not taking the actual logic levels from here. I'm taking them from before the driver that drives the LEDs, which is the correct thing to do. So that's basically it. For the top part, there is a 7414 on top with hysteresis, and that's just to buffer the standalone control signal. This will be on the board itself, so it's not important to buffer it, but it needs to be inverted anyway, because the output enable of this side is the inverted version of the output enable of that side. It's only one output enable signal, that goes to everyone, but in half of the cases, it's an inverted version. So since I had to invert it anyway, I thought I might as well just use it as a local buffer to make sure the signal is strong. Clock and reset, which is active low, therefore the N reset, they come from off-board. The rest is what you've seen before. The only difference is now the output of the result register high can go to the internal bus high, and result register low can go to the internal bus low, driven by these two 254s here, but the same signals go to another 254 that is dedicated to driving the output LEDs. So that's all there is to it. On the board itself, it will be slightly more complicated because when you use deep switches, you need to use resistor networks in order to pull the signals low. Otherwise, you can't switch anything. I will be using more resistor networks to smoothen out the signals whenever there is a bus driver like this one driving a byte into the internal bus. I will put a resistor network in front of it. Here there's no need to do that because it changes nothing in the simulation, but in the real board I will use a 33 ohm resistor network for each one of the bits in order to reduce reflections, to sort of filter out the higher frequency harmonics that get reflected and make the signals more smooth. These 245s, they do have a lot of oomph, and if they are driving a bus which has huge fan out, has branches on all the traces, usually they cause a lot of reflections and ringing on the lines because of that fan out, because of those branches. And because they are strong drivers, the rise time tends to be relatively short, which means that the higher frequency harmonics are rich. There's a lot of higher frequency harmonics every time you switch these signals. So the 33 ohm resistor networks are just meant to dampen those oscillations down, dampen the ringing down a little bit. And that's it. That's the circuit. It's very close to what's going to go on the PCB. Not quite there yet because of all these passives, the resistors, capacitors. I have here, next to me, I'll show you briefly, that's my logbook, here. And this just has my notes of the test vectors I used to test it. It's less than a dozen test vectors. It's actually only 9. Far from exhaustive. Yeah, here. Let me try to put this in a place I can see it. My notebook. Okay, that's much better. I have it open in front of me now. So the first test pattern is 127 minus 83. So this is to test only one side of the ALU because both values fit in 8 bits. So we don't do full width. This will be half width. So let's put in the patterns. First thing, I have to take this. So we are in standalone mode now. And this will be 127, which is 0, 1, 1, 1, 1, 1, 1, 1. And you already see the results in this LED here, because I already set the control bit standalone. So this driver is now active, driving this bus, and of course it goes to the LEDs as well. And the other one is minus 83, but we just put 83, 0, 1, 0, 1, 0, 0, 1, 1. And then we go down in here. Oh yeah, set negative low is already set. So that's already done. And then we go to these two here. Let me put it in auto, then we can see everything. So now the system is in reset. Reset is 0. Let me show it to you, otherwise you can't see it. Here, reset is active low, and it is low. So we just do a reset cycle, and I'll bring the system out of reset. And now when I hit clock, it should compute, and the result should appear here on the low part of the ALU. So we just click clock, rising edge, pop, and low edge again. Let's have a closer look at that. Oops. That's the result. And the result should be 44, so 0, 0, 1, 0, 1, 1, 0, 0. Yeah, that's correct. So that's our first test vector. Now we are going to do, again, 1 byte, but this time we are going to do a subtraction. So I'll put the system in reset again, and we go back up. I mean, we already did subtraction. We will do a subtraction that produces a negative number as a result. That's another important thing to cover. So let's do 52, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0. That's 52, minus 101. So 0, 1, 1, 0, 0, 1, 0, 1, yeah, 0, 1, 1, 0, 0, 1, 0, 1, yeah, that's 101. The result should be minus 49. So we go back to Alto, bring the system out of reset. Reset is now 1, and set negative low is there, set full width is inactive, as it should, so let's just hit the clock. Okay, and let's look at the result. Oops. Result should be minus 49 in 2's complement notation. I already did the conversion. 1, 1, 0, 0, 1, 1, 1, 1, 1. Correct. So that's good too. We are now going to try test vector 3. And now I'm going to do it slightly different. You will see soon what I mean. What I want to do now is do an addition of 24 plus minus 49, which should be a subtraction, but I'm not going to set negative low. So I'll tell the ALU this is an addition, but there will be a 2's complement representation of a negative number in register BL. And it should still give us a correct result of minus 25. So let's check it. 24 is 0, 0, 0, oh, here, 0, 0, 0, 1, 1, 0, 0, 0, 0. That's 24. Plus, but I already turned off set negative low, so this will be an addition, but I'm going to put a 2's complement representation of a negative number on the other side, which is minus 49. Notice that if we are using negative numbers, then the range is from minus 127 to plus 127, because the most significant bit is not a sign, so we don't have the full 8 bits for quantities. We don't go to up to 255 anymore. So minus 49 in 2's complement notation is 1100, 1100, 1111. And that's what we see here in these LED bars, showing what the operands are in manual mode, because standalone is active, is set to 1. Set negative low is not active, so this is an addition. Let's see. Auto. We bring the system out of reset, and now we hit the clock. Nothing happened. What am I doing wrong? Oh, I forgot, I left the system in reset. Okay, we bring it out of reset. Now we hit the clock and we get a result. Let's look at it from close by. The result should be minus 25, which in 2's complement notation is 111, 0, 0, 111. Correct. So that's the third test vector. We are good. We go back here to the dip switches here. Next one is, and now it's another trick. Now it's 24 minus 49, which should be 24 plus 49. But I'm going to do minus, so I'm going to set negative low active. So now it's a subtraction, but it will be subtracting a negative number, which is an addition. So let's see. 24 is the same, that was already there, 0, 0, 0, 1, 1, 0, 0, 0. And then minus 49, oops, yeah, that's the same thing, it's the same number that is already there, minus 49. The difference is that now set negative low is set. So this should actually be an addition and give us 73 as the result. So let's just reset the system, bring it out of reset, and now positive edge of the clock. There. Okay, we have it. Let's look at it. The result should be 73, which is 0, 1, 0, 0, 1, 0, 0, 1. Correct. Next one. Oops. My eyes are not very good. That's why I keep zooming in all the time. Now we are going to test overflow or near overflow. We are going to add 254 plus 1. 254 plus 1. So we will have 1, 1, 1, 1, 1, 1, 0. And then 0, 0, 0, 0, 0, 1. So that should give us all ones and no carry flag. No carry. Oh, I forgot to show you that the carry flags and the 0 flags, they all activate as well. Never mind, never mind. So we go back here, reset the system, bring it out of reset, clock edge low, now clock edge high. This is wrong. Why is it giving me a wrong result? Yeah, it's giving me a wrong result because I am an idiot and I left set negative low active. So this is an addition, not a subtraction, you idiot. So we reset it and then we clock it again. There we go. I can already see here it's all ones. And the carry flag low is not active. It's not active. The sign flag low is active because if you interpret this in 2's complement, then the most significant bit is indeed 1, so it's a negative number. But because this is an addition and there is no chance of there being a negative number, this flag is irrelevant. The sign flag is irrelevant in this case. It's also giving me a 0 flag high for the upper byte, which is okay because everything is indeed 0 there. So the 0 flag logic is working. And we don't have a carry flag here because this is the maximum number that still does fit in 1 byte. So that's okay as well. Let's go for the next test vector. I hope this whole thing is useful to you to watch this process. If you're bored, just skip ahead. We are going to do now a 16-bit operation. We are going to check whether the thing works with set width enable. So set full width. So now we set full width. And this is reset. This is reset. Yeah, the rest is okay. So we set full width. Actually, I want to do a subtraction. I want to subtract 24,351 from 32,767. So I will set a negative low. And we set negative high. It's a 16-bit operation now. So both B high and B low are in negative representation. Now let's put the values. Now I need the whole thing. Yeah. So let's see. On A there should be 0, 1, 1, 1, 1, 1, 1, 1. And then all ones. So this is A. So that's 32,767. And then minus 24,351. That's 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 1. Then we are subtracting B from A. And now we put the clock low, we reset the system, back from reset, and now we post the clock. There we go. So the result should be 8,416, which is, let's look at it more closely. Does it fit if I put magnification 1? We need both. Yeah. Should be 0010, 0010, 0000, 111, and the rest 0. Correct. 8,416. So that was a 16-bit operation. The sign flag, let me see. Sign flag low should be 1, yeah, because this is the most significant bit. That's why you have sign flag low in here. This means exactly nothing because this is not an 8-bit number. This is the low byte of a 16-bit number. So this highest order bit here is not a sign at all, but the logic is the logic. It's when we construct the instruction set architecture and the coding of the instructions, we will make sure we will ignore this. That's all there is to it. We also have carry flag low high, which makes sense because this is a 16-bit operation, so the carry out here is active. Light green means it's 1. We actually don't need the LEDs. I'm cheating. Dark green is 0, light green is 1 in this simulator. It's very easy to simulate even without hanging models of LEDs. But it's a 16-bit operation, so there was a carry. That's okay. Just reset the system now. Out of reset. Now the next one will be a subtraction, 16-bit subtraction again. So we have set negative low enabled, set negative high enabled, set full width enabled. That's correct. We will keep the first operand the same. That's 32,767. But now we are going to subtract 8,666 just to have another value. No mystery about this. So that's 0010, 000. Oh, what am I doing? It's incorrect. That's not the place to change. This is the low bit of A, and I have to change B. So A is 011111111, correct? And now B is 0101. No, 0010. That's what we want now. 0001. 0001. 1111. 01. 1010. 1010. So that should be 32,767 here and here, and 8,666 here and here. Let me just double check it. Correct. That is correct. Just going to reset it again just for safety. And now we just click the clock. We get the result. And now let's have a look at the result. We should have the result as 24,101, which is 0101, 0101, 1110, 1110, 0010, 0010, 0101, 0101. Correct. Another check. Now let's do a 16-bit subtraction with a negative result now. So we keep the set negatives as they are, set full width still the same. We just change the operands now. So let's go there and change it. First operand is 28,677, which is 0111, and then 0000, and then 0000, 0101, 0101. So that's our A, which is 28,677. Let me cross-check here on the LEDs. 0, 1, 1, 0, 0, 0. 0, 0, 0, 0, 1, 0, 1, correct. And the operand B is 32,100. And we are going to perform a subtraction, so the result should be negative. It should be minus 3,423. So let's set the other operand. Should be 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 1, and then 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, oh, 0, 1, 0, 0. And let me cross-check operand B. Correct. Auto. Let's give it another reset. Bring the clock down. And now just hit the clock and we get a result. Now let's make it a little bigger because I have poor eyesight. Let's look at the LEDs. It's now a 16-bit number here, which should be minus 3,423 in 2's complement notation. So it should be 0, 0, no, let me check again. 1, 1, 1, 1, 0, 0, 1, 0, yep, and then 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, correct. Let's now do an addition that uses all the bits. So we are going to set negative high inactive, set negative low inactive, set full width still there. It's going to be a 16-bit operation, so still full width. And now the operands change. The operands are now 20,000 plus 12,767. So 20,000 plus 12,767, which should give everything 1 except the most significant bit. So let's see. 20,000 is 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, and then the rest is 0. So let me cross-check this. First one is correct. Now operand B is 12,767, which is 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1. Let me cross-check this. So that's register B. Correct. Go to auto. We reset the system, bring it out of reset, bring the clock low so we can have a positive transition, and hit the clock. Now let's go down and have a look at the result. So again, 16-bit result. Yeah, only the first bit should be 0 and everything else should be 1. So the sign flag high should be 0. Sign flag high is 0. 0 flag should be inactive because there's no 0 in there. The carry flag, sign flag low is high, of course, because this bit is 1. So if you were to interpret it as 2's complement, you would have a sign there. But this is a 16-bit result, so that's not the way to interpret it. That's correct. Yep. Yep, it's all looking good. Now, what I had done before, but I don't have here on my notes, is to use two operations at the same time, which is trivial because the circuits are identical, but just for the sake of the video, let's do that. So set full width will now be inactive, so it's now two separate 8-bit ALUs, and I will just program the operations we did in the beginning. I will program the same operation on both sides, so we see that the thing does operate as two separate ALUs. And the first was 127 minus 83. Let's do it on both sides. And then we put both sign flags active, because it's a subtraction on both sides. Sign flag high, not sign flag, set negative high and set negative low. I'm not talking about the flags, I'm talking about the operation. This should be a subtraction, subtracting a positive number from another positive number. 127 minus 83 on both sides, so we should get 44 on both sides. Let's see if that's the case. We reset the system, bring it out of reset, clock low, and now on the rising edge we should get the result. There we go. The result is identical on both sides. I can already see it. Let's look at it closer. Now the result should be 44, which is 0010, correct? 1100. 110, correct. Let's continue to do the same thing now, but let's do a subtraction. Let's do sorry, this was already a subtraction. Let's do a subtraction that leads to a negative number as result. So 52 minus 101, which should be minus 49. So let's change the operands. It's still a subtraction on both sides, so set negative high, set negative low. No full width. These are two parallel 8-bit operations. All good. Let's reset it. Clock low, clock high. And let's look at the result. The result should be minus 49 in 2's complement notation, which is 1100, and then the rest is 1. 1100, the rest is 1. 1100, the rest is 1. Correct. And now this is 2's complement notation, so the sign flag is relevant now. Let's see, sign flag low is active, correct. Low has a negative number, and sign flag high is active, correct. It's also a negative number on the high part of the ALU, both are minus 49. They are not zero, so the zero flags are low, there's no carry. Let's do one more. I hope I'm not boring you. I already tested all this before. Let's do 24 plus minus 49. So we do an addition as operation. So we don't set negative high and we don't set negative low. This is an addition now. But then the first operand will be 24 and the second operand will be minus 49. Let's see if this is going to work. We have to interpret the result then in 2's complement. I'm not setting negative high or setting negative low, so this is an addition. And because one of the operands is negative, we should have minus 25, so we should interpret the end result in 2's complement, not as a positive number. You can interpret it as a positive number, but that will be a wrong interpretation in this context. So resetting the system, bringing it out of reset, clock low, clock high. Let's have a look. Minus 25 is 3 times 1, 0, 0, and 3 times 1. Correct, on both sides. And the sign flags are active on both sides. And there is no zero flag and no carry flag. Correct. What else can we do? We can try an overflow. We can let's do 255 plus 1 on both sides. Then we should see the carry flag. Yeah, this is addition. I'll set as addition. So I just put 1, 1, 1, 1, 1, 1 on the first operand on both sides. and it doesn't matter what we add now. Let's add only 1, so it would have to be 256. So it will not be, it will be all zeros, and the carry flag will be high. That's what we should have. 0, 0, 0, 0, 0. So I'm trying to add 1 to 255, which should be 0 with both carry flags visible or active. Resetting, bring out the reset, clock low. Is it all good? Yeah, all good. Clock high. There we go. There we go. Exactly as it should. The results are zeros because 256 is 1 followed by 8 zeros. What you're seeing here are the 8 zeros, and the carries, the carry flags are active. Carry flag low is active, carry flag high is active, and then we still get the 0 flags because that byte is indeed 0. Yeah, this is it. It's enough for testing. The point of doing this, as I'm sure I'm repeating myself, but I'll say this again, is I want to make sure that my netlist, my interconnect, is correct, because that's what I'm going to export a netlist to a schematic diagram and put on the PCB. That's the whole point of this test, is to make sure the PCB will be correct. It's very nice of this tool that it has models for all these chips. Some of these chips are fairly complex internally. I mean, the 74283s, the ALUs, they have dozens of gates inside. It's very handy to have this model, and this is another reason why you definitely don't want to do a schematic based on individual gates. It's a waste of time and defeats the purpose, because we know this chip works. Why am I going to go through the trouble of putting together the dozens of gates inside this chip to verify that they work? I know the chip works. 74 series logic has been sold since the late 60s, I think 1969 or something. We know they work. I don't need to simulate them internally by building their internal structure. I need to simulate how I interconnect them. That's the point of this whole exercise. I was planning to show you today also the migration to the CAD tool with which I designed the board and the schematic entry that I've used there. But because of my rant in the beginning of this episode, the episode is long enough by now. I showed you lots of test vectors as well. So I will leave it for next time. Next time we are going to go through the actual schematics and perhaps even the PCB design. Yeah, let's do that. Let's go through the actual schematics, the physical PCB design, because electronics is a physical thing, unlike what the dilettantes might make it look. Electronics is not an abstract world of Boolean operations. Those abstractions are useful for design, but at the end of the day, this is, it's silicon and electrons moving. So let's look at the actual PCB design that deals with those electrons and deals with the silicon chips in it. I'll explain what I did. And then the episode after that, we will populate the first board and see if it works. I haven't done it yet. I don't know whether it will work. The simulation works, so unless I made a translation error, which is possible, because there is no automatic export from Logisim to EasyEDA, which is the tool I normally use because it's freely available to everybody. Nobody needs to pay a license. There's a possibility I made a mistake, but we'll see. Before I find out, I will show you what I did as far as the board is concerned, mistakes and all, if there are any. All right, I hope you're not too tired. Thanks for watching, and I will see you next time. Take care.